Hello, I'm John Chivacco, the co-chair of the NY-GEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NY-GEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NY-GEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NY-GEO at the appropriate membership level with details available at our website. The live recording from the NY-GEO 2023 conference will start in just a moment. Thanks so much for listening.
I created this title slide to kind of get a little bit of a buzz going with my driller buddies, and suggested that, well, maybe there's some different ways that we need to be thinking about making all this stuff work. And there was no offense intended. And I'll say that in my 4 decades of designing systems, 99% of them are vertical closed loop. But what I want to share today, it's a variety of options to give you options, more tools in your toolbox. And I was at an excellent presentation just before lunch that spoke about the value of energy storage in the ground. And they were doing the math on electrical batteries and charging and discharging batteries, and then the analogous thermal storage, where a heating load takes heat out of the ground in the winter and a cooling load puts it back in the summer. And big dollars when you start doing the analogous comparison to the electrical round trip of energy with an electrical battery and a heat pump and a thermal storage like a vertical closed loop system. The numbers get pretty staggering. And I think it's a math that as an industry we probably ought to pay more attention to, because I think it would tell our story more effectively in the marketplace. So challenge a couple of you to think about that. Yeah, I mentioned 40 years. My partner wears a ball cap that says older than dirt, which is appropriate for our industry. But I was on a tour yesterday, touring Albany, and we were in Sheridan Hollow, where we have a district heat pump feasibility study going, and drove past the state campus, the Empire Building campus, and I pointed at one of the high rises and said, you know, as a kid, right out of college, I did an energy audit on that building 43 years ago, and I had absolutely no clue. I got into that big chiller plant there that was pumping 70,000 gallons a minute of condenser water, and no clue. But a lot has happened in 40 years, and I'm excited at some of the things we're looking at here in New York with NYSERDA and the teams that we put together on really electrifying some major systems, reaching out to LMI neighborhoods and raising the quality of life. And in that process, what I want to equip everybody that gets involved in this process with vertical closed loops are not the only thing. There are other ways that we may be able to enhance the system, optimize the system, either first cost wise or energy wise. Now, got a few objectives. Identify these alternative options. If vertical or horizontal closed loops might not be the best, or we just can't fit enough of them in, which is something we're looking at Sheridan Hollow. You got a vacant lot here and an old parking lot there and a little green strip here, and how do you make this work? We're going to talk about advantages and disadvantages, the kind of stuff that can get you into trouble and you need to watch out for if you consider these systems. Talk about equipment. Some of these have some specialized equipment that's only available from a few sources. And, you know, I'll do the disclaimer here. I'm going to use names of manufacturers. That may be a bit offensive to some, but I want to say that that's not an endorsement from Steve or from NY-GEO or ASHRAE or anybody else, but I think it's important. Too many times I've sat through presentations and somebody has shown something that's pretty cool on the screen and I can't figure out where they got it or where to get information. So I put, excuse me, at least put some names on the screens where the images come from, and a Google search will probably help you out as you seek more information. The idea, alternative thoughts, and truly in our industry, if we only have a hammer in our toolbox, every project's going to look like a nail. If we only have the ability to do vertical closed loop and maybe not mix it with other things, we may not give our clients the best solution. So I've always liked that little phrase. We're going to talk through a whole series of options here. Of course, you always have to talk about air source heat pumps because that's what everybody wants to talk about and how bad they are and how we should avoid them if we can. Wastewater. Wastewater can be a biggie, especially in the urban areas that we're seeking to transfer and do beneficial electrification with. And we're going to talk about several different levels or capacities at like the campus level, central plant, district energy plant, 4,000 tons, something like that. Building level could be 15, 20, 150 tons, 200 tons. Doing it at the collection network. So there's maybe a couple of things you may not have seen that I'll share with you. And well, what if we transferred thermal energy in the wastewater pipe network and did it differently? And then finally at the appliance level, some options that are there that you can apply in a home or a commercial building. Stormwater, again, referencing our project yesterday in Sheridan Hollow, those of you that are familiar with the area, it's a hilly area that has a very significant stormwater management issue. And when it rains in Sheridan Hollow, there's flooding at the bottom of the hill. And so there's significant volumes of basically water at wet bulb temperatures that could be available during those storm events. We're going to talk about, well, is there a way to capture those, use those in a beneficial way so that the stormwater issue is reduced and we get some beneficial thermal value, and then we release it in a manner that doesn't cause flooding. Talk about that. Surface water. There's some cool options here with bodies of water. We got the Hudson River, and we'll talk about when we get into bodies of water that are governed by the Corps of Engineers, what does that do to project steps that you have to work through. And then we'll talk about a couple different types of heat transfer systems for surface water applications, some that you've seen again and again and again, and I think one that you may not have seen. So stand by for some new stuff. Potable water is one that we don't talk about a lot, but I'll share a project that was done in New York, very successful project in 2015, and a school, and Don Penn designed it, and it's an excellent project, and it's been running for a number of years, providing a lot of benefit, and it's a model that I think is one that could be applied in many applications, given the right conditions. Irrigation water. We, back in Michigan, I designed a lot of K-12 schools, and a lot of those schools had big football fields and soccer fields, et cetera, that in the summertime, they irrigated many, many, many hours a night, thousands of gallons. And when we had schools that had imbalanced loads, i.e. they had a little more air conditioning that was putting heat into the ground than we really liked, we looked at adding heat exchangers to the irrigation system. And One high school I did, it was like running a 40-ton cooling tower for 8 or 10 hours a night. But pretty much at no additional cost other than the pump energy to push some water through a heat exchanger. We'll talk about that. And finally, we'll close on thermal energy storage and some of the various ways that benefits our system. I put this slide in here just because I thought it was cool. I mean, we got some water droplets going on in there, and they're moving around. And anyway, I'm easily fascinated as an engineer. Thermal temperature or ambient temperature loops, and this is a very busy diagram, and I apologize for that. What we're showing here is really the backbone, and I've been reminded to speak into the mic because we're being recorded, the backbone of a lot of the district scale systems that we're talking about, not only in New York, but we're working on projects in Utah and Colorado and Texas and Oregon and Minnesota and elsewhere, Maine, that shows how these various heat sources and sinks, and we got a couple buildings connected here as well, might play with each other. So if we start at the top, we show a couple of pumps. Usually these are the main circulating pumps for the ambient temperature loop, and this is a one-pipe system, which again is different for a lot of people to get their head around. Usually you have a supply line and a return line. Well, here we have one pipe that buildings pull water out of, warm it up or cool it down, and they put it back in. What's the advantage of a one-pipe system over a two-pipe system? Number one, diversity. We can capture much, much, much more diversity in a one-pipe system than we can with a two-pipe, because the building flows mix with each other in that pipe. My partner Kerry can talk about a university project that he's been working on for a couple of decades. And when they first started converting that campus, they had about 250 bore feet per ton. That's how much vertical pipe in the ground, 250 bore feet per ton, that they needed to keep that campus under control. As the system has grown, that's dropped down to under 80 bore feet per ton. So we've added a bunch of load, but not much bore field. And they haven't run the boilers there for like 10 years. So it's, as we're learning about these systems, and if we're able to connect multiple building types in multiple areas, is there a data center nearby? Is there a large government complex cooled by water-cooled chillers that borrow water from the Hudson River and makes that water really, really, really warm, and then we put it back into the river? Could we use that to recharge those residential cold bore fields in the summertime and maybe benefit the energy use of that campus? Are there things like that? So we start at the top, the main pumps. We work our way clockwise. There's something there called a PV thermal collector, which is solar photovoltaics, which generate electricity, and then there's a hydronic panel behind the PV that when the sun shines, we circulate water through there. We can grab some low-grade energy, 100, 120, 130 degrees, if that's beneficial, and we can stick that in our loop. It also makes our PV panel slightly more efficient, so we get a little more, maybe 3 to 7% more electrical production if we keep those panels a little cooler. A neat feature in this configuration is if you have the opposite problem, that your loop is too warm in the summertime, at night, when the sun has gone down and if the air cools down a little bit, you can use these to reject heat. Kind of like a cooling tower, but without fans, without spray pumps, without water, without chemical treatment, without noise, vibration, Legionella, et cetera. Next system down, about 2 o'clock. That's a 6-pipe chiller feeding a building. So it has 2 pipes connected to an ambient temperature loop, and it's recovering energy internally or transferring energy internally between the chilled water line and a hot water line. When those are in balance, heating load equals cooling load, nothing happens with the ambient temperature loop. If it needs more cooling and there's insufficient heating, It starts to take water from the ambient temperature loop, lowers that water temperature a little bit, and that goes back into the loop. And that's, and several of the folks that are here at this conference, the manufacturers, make that type of equipment. And you can talk to some of them on the floor here. As we drop down a little bit further, there's our air source heat pump. And we'll talk about that some more in just a moment, but it can do the job. It can put heat in a loop, it can take heat out of the loop, and if there's creative ways that you can make that very efficient, or have very inexpensive power that's feeding it, that may be an option. Or if you've got to take a lot of heat out in a short period of time. I've been involved with projects where a bore field, a vertical bore field, has failed because it got too hot. And usually they get too hot because either they're under-designed or they weren't controlled right, or I had one automotive plant where they went from a one-shift operation to a two-shift operation and added a bunch more water-cooled equipment, and they heated that bore field up to 120 degrees. And the only way to cool it down with any speed was to rent an air-cooled chiller. And you don't like to do that, but that's a way to do it. Going down the pipe, on the right, we see a bunch of distributed unitary heat pumps scattered around the building. That's just another option for our building. The 4-pipe, 6-pipe system above it, those hot water pipes, chill water pipes could be feeding air handling units, VAV systems, fan coils, any variety of terminal devices. And for the engineers in the room, again, I'm always encouraging to design, if you're going to design for hot water heating, use the coolest hot water you can get by with. If you can do it with 120 degree, 125 degree, that's really going to boost your heat pump efficiency and make things work well. And it can be done. If you want to know more about that, I recently completed a webinar for ASHRAE and NYSERDA that was broadcast a few weeks ago, and I talk a lot about how to convert these legacy buildings that were designed for 180 degree hot water, et cetera. As we keep sliding down farther, the next thing that's connected on the left-hand side, I think that's a squint at the screen, stormwater. Yes, underground stormwater reservoir. And like we mentioned on the Sheridan Hollow project, if we could redirect hundreds of cubic feet of stormwater after an event, hold on to it and get a beneficial thermal something, either dump heat into it or pull heat out of it, and connect it via a heat exchanger to our ambient temperature loop, and then release it in a controlled manner to the stormwater distribution system. The next one down below that we'll talk about is wastewater energy systems. And again, we'll talk about those in 4 different configurations. Down at the bottom, right-hand corner, the industry favorite based on the number or the percentage that are installed is the vertical closed loop. We all know that. We have a bunch of people at the show, at the conference, that do that every day. We have innovative pipe to stick in the ground to enhance heat transfer. And as long as we dot our I's and cross our T's, design right, test our conditions first, that's a fantastic system. And of all the systems up on the screen right now, really the lowest number of moving parts. We got pipe in the ground that should be there 50 or 100 years with very, very little maintenance required. The next one, so I got to put my cheaters on again. Oh, I think we might call that a pump and dump system. And so you've got well water passing through a plate and frame heat exchanger, then back to some surface water or diffusion well, and that technology has been around forever and ever and ever. Well water is one of those things that you have to pay attention to, because well water chemistry can be a challenge in certain areas. Its mineral content can be a challenge in certain areas. So you got to think about, if you're going to do it, how are you going to manage those things? And are you going to separate your well water from your building loop water, or do the old pump and dump systems where the well water circulates all the way through the heat pump and then it's discharged? And I designed a system, a commercial building 35 years ago, that is a closed loop system, closed open loop system. So closed loop, traditional heat pumps, circulating pumps. It was an old industrial building in Grand Haven, Michigan, piano factory. They did retail and restaurants on the first level, and then condos and apartments on the upper levels. It's great because the retail generated heat all winter, and the residential needed heat all winter. And the way it worked was really simple. And this was back in the mid 80s. We didn't have really sophisticated electronic controls. So we had 5 wells, 5 production water wells, and 5 discharge drains that the city of Grand Haven allowed us to connect to the storm sewer, because we were about 100 yards from the Grand River. And as that building loop got too hot or too cold, those drain valves would start to open in sequence. And every time a drain valve would open, a pressure switch would turn on a well pump to maintain the system pressure. And so let the hot water out and pump some cool water in and stage that up and down as needed. And it's run for, jeepers, 4 decades. A lot of the old heat pumps from the original project are still there, it's still running, which is a testament to this type of technology. The good groundwater quality there. The only issue we had is that's very sandy there at Lake Michigan, and sand entrained in the water over time would chew up the pump impellers. So pumps and pump impellers got replaced every decade or 15 years or so. But other than that, it's still there. It'd be probably a great case study for somebody. The next system to the left that is one where the heat exchanger is taken out of the building and put in a well casing. And the advantage of that is the groundwater never leaves the ground. Groundwater passes through a heat exchanger that the building loop is separated from the groundwater, double wall heat exchanger, exchanges its temperature, its thermal, and then the groundwater is returned to the aquifer either through a diffusion well or in a surface body. And got a nice sized commercial project with that going in Michigan that'll be completed here this summer, and maybe next year we can have a case study on how well that's working out. Following that one is just, I think, a big tank of water. Surface water heat exchanger. So we're going to talk about that and the 2 different classes of heat exchangers that we might use depending on the application and how much room we have. The next one up from there is a combined heat and power system. So that's a gas-fired unit making electricity, and there's going to be waste heat. And in certain circumstances, that may make sense. In areas where there's going to be 0 natural gas or fossil gas, then that doesn't make sense. But it's something to consider. Above that is a closed-circuit cooling tower. Works great, very efficient. If a heat pump has a COP of 2 or 3 or 5, a typical cooling tower has a COP on the order of, or rather an EER of around 250. They can be quite efficient at transferring thermal energy. But you've got chemical treatment, water makeup, noise, sound, vibration, potential for Legionella, et cetera. Not as popular as some things. Next item up is a simple boiler. Just if we got a residential heating dominated application and 2% of the year we just got to get some heat in there somehow, that's an option you may have to consider. And then that last one is just thermal energy storage. Whether it be phase change materials, above ground stratified water tanks, below grade water tanks, big tanks in candle making factories. There's ways to use these things. All right, let's get into it. Oh, another fun one. This is the Zen moment as you just, okay. Water source or air source heat pumps, yeah, they work. The issue here is you gotta be smart. And so I've taken manufacturers' data, this is real data, and what is their heating capacity versus outside air temperature. You can see it's dropping as it gets cold. And then what is its efficiency as the outside air temperature drops. And we're down to about a third of the capacity heating-wise at zero. And thankfully, Cold Climate Heat Pump Initiative, they're working on equipment that goes to minus 22, but look at the efficiency and the capacity. Just because it runs at minus 22 doesn't mean it pencils out. In this particular case, the COP is 1.5, a little higher than I've seen on others. Others are 1.1, 1.2, et cetera. Now, the biggest thing I encourage engineers and contractors as they want to apply this equipment is get real performance data, and especially get cold temperature performance data if you're designing in parts of the country that get cold and you need heat. And worked on a senior living facility in northern Michigan a number of years ago that they had a string of minus 22 degree Fahrenheit days, like 5 in a row. And the air source VRF units couldn't get the resident rooms above 62 degrees. And if you've ever been in a rest home, folks there like it warm, and 62 is not warm. And that could have been solved. They could have had auxiliary heat either in their dedicated outside air system to bump that ventilation air into the room to a higher temperature, or some distributed fin tube, or something like that. But not good. So make sure you know what you're going to do. And if you're using, what's your heating capacity? What are you going to do? Are you going to add auxiliary heat, or are you going to triple the size of the unit? And then that means triple the electrical feed. It goes on and on and on. At the low temps, what is the consumption going to be? Can your building handle it? Can your grid handle it? What about snow drifts and defrost cycles? Again, going to my senior living facility, when those units, which were wall-mounted cassettes, went into defrost, they blew cool air on the residents. So they would go from moderately warm air, say 95, to 65, 60 degree air blowing on them for a couple minutes, and it was a real comfort issue. So units now are getting better about handling the defrost cycle, but really pay attention to that. And I've seen units all over the Midwest with snow drifts and then big icebergs built up underneath that might be 12, 18 inches tall. Make sure you get these units off the ground if they're on a pad, so there's room for ice to accumulate underneath. And my goodness, if you get a snowstorm and it drifts, you got to shovel them out. They just are not going to work. The other part of this is, ASHRAE's done a lot of studies, and in general, air-cooled stuff lasts less than water-cooled stuff. So ASHRAE would say 15 years on air source heat pumps, air-cooled chillers, and 24 years plus on water source heat pumps and ground source heat pumps. So as you think about the question? Yes, please. Yeah, go ahead.
Hold on. I'm looking at this list. Does this list consider units that are variable speeds compressors, or is that something different?
It's an excellent question. And ASHRAE's data does not. And so this is an ongoing thing with ASHRAE, and they have to fund various research projects. As far as I know, all the current ASHRAE data is single stage stuff, on, off, bang on, bang off. I think you could argue that inverter-driven stuff is going to last longer. May have a few more things that can go sideways, but at least it takes the stresses out of a hard start. Good question. I would love to see somebody pilot some new research for these numbers. Okay, Zen moment. Just think of all the things that would flush down a pipe. All the energy there. Okay. So these can get really, really, really large. There's two big players in the world, Shark Energy and Huber. They've both been around for quite a while. Both have big systems. You know, the project up in Vancouver, I think there might be 8,000 tons. And effluent generally is 65 to 75 degrees year-round, from Texas to Maine. The big thing, if you're thinking that, wow, there's a 60-inch sanitary main running in front of my project, and usually the city can say, okay, this is our average flow, cubic feet per day, here's our peak flow, cubic feet per day. And you can start to do the math, and you can get a lot of energy. First question, is this a dedicated sanitary sewer, or is it a combined storm sanitary sewer? And what you have to watch, especially in northern applications like New York, if it's a combined system where I flush the toilet and the snow's melting outside, that 75-degree water from my home is going to mix with 35-degree water off the street, and it's going to get cold. Now, the potential saving on that type of a deal is you may have miles and miles of horizontal concrete pipe that will help to warm that up. It's surrounded by soil temperature that may be 50 degrees. And so it may not be so cold all the way, but it reduces the capacity. And there have been some applications that we have looked at where there's a very significant stormwater impact, and it just doesn't make sense to do it at the central plant. Now, if it doesn't make sense to do it there, and I'll just add on these, I know on the shark side, maintenance is pretty minimal. It seems to be quite robust. And really all this is it's creating a condenser water flow stream that you hook to like a 6-pipe heat pump, and then you either pump heat out of it or you pump heat into it. King County, Seattle, they have written their ordinances there to make it legal to connect to their wastewater distribution system. They do some incentives on that. They want every new building built there to have the provision to put it in and to actually do a study. Does it make sense to do it right away? And I think that's the first county. And then they monetize it. And so they're doing it on a BTU basis, and how many BTUs you put into the system versus how many BTUs you take out of the system, you pay. You actually pay both ways. But you're getting rid of a cooling tower and all of its associated costs, and you're potentially getting rid of a boiler and all of its associated costs, and it should be an environmentally much friendlier system. And so what if you can't do this more central? If you go down to the building level, then there's more options, you know, in this 15 to 25 ton type range. And the big ones tend to operate continuously, so they process flow all the time. These smaller ones tend to operate in batch. So there's a tank inside that box in the upper right-hand corner that's insulated and surrounded by refrigeration piping embedded in the walls. 300 gallons, depending on the size of the tank. Black water comes in, compressor comes on, it pulls heat out of that waste until that waste reaches a certain temperature, and it's pumping heat into your, say, potable hot water system. And then when it's done with the cycle, it discharges it to the wastewater system. This particular model also has the ability to pull heat out of condenser water loops, cooling water loops, chilled water loops. So if you have insufficient wastewater load at time, it can pick between which one is warmest, where do I get the most benefit. And these are the nice parts, all factory built, factory controls. They added COVID testing ports on here, so it'll keep samples, and that's being used in some cities to kind of track where there may be COVID circumstances happening. So worth looking at. Now, maybe some stuff you may or may not have looked at before. This is a company out of Canada, Ontario, and they have embedded pipe inside the wastewater main. And it's sectional mains, and then you connect that pipe together, and heat pump loop fluid, usually a glycol, flows from the heat pump in the house out through those loops that are in the concrete, and you've got wastewater laying on the bottom, quarter of that pipe. Seldom are these pipes filled to the top. Usually you're only going to get heat transfer out of the bottom. And they suggest, that you do a hybrid system here. So they have a single vertical closed loop, and then they say 100 feet of this at-source energy pipe would be enough for an average house. And if you look them up, they have a lot of cost information if you ever want to run the numbers. They also sell a solar PV hybrid thermal collector that can grab thermal energy in addition to the electricity it generates. A little less complicated, and you may have seen some of these, but these have been around for quite a while. And the one on the left is classified as a thin film heat recovery device. It's applied vertically, and when drain water comes down, and usually they prefer to just have this hooked to gray water, like the showers and sinks, maybe not the toilets as much, but it's 3 and 4 inch copper, it's flat inside. You could probably do it. As the water enters the top, it attaches itself to the circumference, and you get a real thin film of water that covers the whole circumference of the pipe, and you run cold water in on the outside in a separate loop. The two water streams, the wastewater never mixes with the other water, and you can use this to preheat your domestic hot water. And they sell these things at like Home Depot. And you can stack them up, put them together. But this, excuse me, this model does not work well horizontally. It's meant for that thin film. Now the ones on the left are interesting. The middle one is a heat exchanger intended to clamp on cast iron pipe. I think 3 inches to 12 inches in diameter. And that could be interesting, as you get into bigger multifamily, commercial type stuff, if there's sufficient wastewater flow. Simple device, no moving parts, might be relatively inexpensive. The one on the far right is intended for residential applications, and it's a full horizontal one. If you don't have a basement with enough vertical height that you can do the left-handed one, that other one is an option. And I've not ever run the numbers on these, but what if you did 2 of these, and maybe the first to preheat domestic hot water, and then the last, if you were a really heating dominant home, just get a little bit of extra heat there that goes into the heat pump loop. These are not crazy expensive. We're talking hundreds of dollars. Might be an interesting experiment sometime. Zen moment. Just relax. It's all good. Okay. Stormwater, as we talked about Sheridan Hollow, I think the real key here is you have a stormwater event, you gotta get it to where you can hold it without flooding the street. So you have to have the infrastructure that captures at the street level, big enough pipe, and then get it to where it's gonna go. We know how to do that. Then there are all kinds of HDPE, pre-engineered, prefabricated structures that can go under parking lots, in just underground, and period. If you want oil separation, grease separation built in, pump pits, it says image provided by Uponor. If you Google Uponor and their stormwater stuff, none of it's in English, but they have really, really cool stuff. And there are other systems that we use under parking lots that are kind of like half cylinders. And what you do is you accumulate the water, and if it's at a temperature that is of value to you, either it's warm enough or it's cool enough, you pump it out through a heat exchanger that's then connected to your ambient temperature loop. Then that discharge would then go to your storm sewer. or back into the tank, depending on the system configuration. And then at the opportune time, the tank either releases itself automatically or could be managed by the Stormwater Authority. In places where you've got significant elevation changes, like here in Albany, this may solve several problems. But it takes a parking lot. It takes a good size area to get a volume underground and ready to go. Cruising along and nobody's fallen out of their chair yet. Thank you. All right. Surface water. I've always enjoyed these systems. Coming from Michigan, you know, we got lots of lakes, lots of rivers, and so this is the one that many of you will be most familiar with, the plate type heat exchanger. I have two different companies here, AWeb Supply and Major Geothermal, both great companies. And if we set this in a pond with no real current in it, its heat transfer capability is driven by convection, right? Warm water comes inside those panels. Those are hollow panels. Warm water flows through it. It heats up the water outside the panel, and that water is more buoyant, so that water goes up, and then it pulls cooler water from underneath, and that convection cycle continues. One mistake that I have seen engineers do at times is they find the deepest part of the pond, and they drop it in the hole. And the problem, you shouldn't do that because your cold water, after it's given up some energy, has no place to go. So, if you will, the bottom of the bathtub gets colder and colder. So your best bet is if you've got a pond with a sloped side that will allow that cold water as it drops off to then flow down to a deeper part of your surface body of water. The cycle is just the opposite in the summertime, but although it's going up, it dissipates a little easier. But these have been used on some major applications, big airports, I think some at Disney, big houses. We've got some in West Michigan in a river, and if you've got river current, now you're into a different story. Now you've bumped your heat transfer capability a bit. Depending on the river, though, you're either engaging the Corps of Engineers. If it's a navigable river, you need to think that through. It's not a horrible process, but it's a process. And the other things that you have to think about, whether it's surface water or like a lake or a river, boats. You know, am I going to create a problem? Is this in an area people anchor a lot and they're going to catch this with anchors? Some people say this is a great fish habitat thing because fish kind of like to swimming around. That might be a plus. There's been one installed in Lake Michigan where we have a zebra mussel issue, and it's been there for a decade on a Coast Guard station, I think in Chicago. And talking to Alan at AWeb, he says, no problem. We're just not having a problem with encrustation, and because that would reduce heat transfer. Okay, next one that you probably haven't seen. Oh, question somewhere. Did I see a question? Oh, okay. I love it when that happens. This one is an interesting one. This is a forced flow heat exchanger. So it has a submersible pump, think Grundfos well pump or something like that, on a carriage that is lowered into a surface body of water. There's a structural cable and three pipes that go down to that unit along with electrical. And it then pulls water out of the bottom, the bottommost entrance, through the heat exchanger, then up a pipe that then it goes somewhere else. Either it's discharged somewhere else in the surface body or it's discharged back into the aquifer. The real advantage here is it's really small for the amount of heat transfer that you can get. And of course, disadvantage, yeah, it has power and moving parts, but this may fit, say, under a small boat dock, whereas a big plate type unit may not. And here's some different configurations of that unit. This unit's not at the show, but you can talk to the inventor and manufacturer over in the other room. They are here. And I think it's going to open up some very interesting applications. The heat exchanger is food and pharmaceutical grade stainless steel, polished really, really high. I said my concern was biofilms and stuff attaching to that heat exchanger. And Mandar indicates that in India, this has just not been a problem. And they like things like briny water. And so I think of Florida could be a really interesting application for this technology. So hopefully, maybe next year we'll have some case studies of how well this technology is working out. Potable water. I have to do the pause. Okay. This is a fun little school, 40,000 square foot elementary school, Valley Stream, New York. Again, this project was done in 2015. And quite simply, the city water, potable water main in the street, they take water out of that main. It passes through a double wall heat exchanger, so that prevents any chance of heat pump fluid coming in contact with the potable water fluid. And actually the heat pump loop here is a water glycol loop. And then they have geothermal heat pumps scattered around the school building. And 133 tons peak capacity. 250 GPM is the maximum flow through the domestic hot water heat exchanger. Water glycol to each of the heat pumps. And 2015, the articles I was reading that was saving around $40,000 a year versus their old gas boiler regular air conditioning system. So it was quite a success overall. The other thing is, everybody worries about we're going to mess with the water temperature in the main. And that main's got thousands of gallons a minute flowing through it. I think it was less than a degree. It might have been a few tenths of a degree that once it mixed, then there was minimal change. But think again like the wastewater collection network being a horizontal heat exchanger underground. This city water main is a horizontal heat exchanger underground as well. So it's constantly trying to reach thermal equilibrium with the surrounding soil. So it's either, if it's too cold, it's giving up heat, or taking heat from the soil, if you will. And if it's too hot, it's trying to push heat into the soil as well. And so I think as I've talked to municipalities about this, usually the biggest hurdle is regulatory or perception that we're putting potable water at risk. And when we address all those things with double wall heat exchangers and everything else, and show that this is very safe, I think it could solve problems. And I'll come back to that. Irrigation. Yeah.
You said the hardest part is the regulatory part, but for that project, do you know any details about how it got approved?
I don't. I haven't talked to Don, and
okay. 'Cause it seems like a solution for everywhere. I mean,
yeah. I know when I've knocked on the doors, generally it's no, you can't touch our water system. It's their perception of liability is very, very high. Even when we say this could become an additional revenue stream, and you could become a thermal utility, and it's easy. I haven't asked, though, in the last couple of years, and I think with the push for beneficial decarbonization, beneficial electrification, cities making huge carbon reduction goals, this is just another conversation that we ought to have. And I agree. I think it could be used in a lot of applications. And so, yes. Perfect. I have only 40 slides left. No, almost done. Irrigation water, I mentioned this earlier, but nothing more than if you've got, the application I had, the city water was running 55, 60 degrees, and that loop was running elevated temperatures, 85, 90 degrees, and so just a pump and a heat exchanger, and when the irrigation system went on, that pump on the right just pumped water out of the heat pump loop and back into the heat pump loop, and it kind of trickle charged the bore field. And every night it was a freebie thing, and the grass didn't care if the water was 80 degrees instead of 65. There may be other industries, you know, would I do this in a grow house or something like that? I don't know the intricacies of growing different kinds of plants, and they may be much more sensitive to temperature than regular grass being irrigated. But it's one of those things, if you got a problem, maybe you can fix it that way. And maybe that water's not going to irrigation. Maybe it's going to a commercial process to flush something, you know, and then, but before you release it down the drain, you know, that's another application of like the shark piranhas. Breweries, distilleries do a tremendous amount of hot water cleaning. They have to get that water temperature down to below 140 before it goes into the city drain. Put a unit in there and capture that hot water to preheat your next batch of cleaning water. So it doesn't just have to be stuff coming out of toilets. You can have industrial processes that fit as well. And this one is I just want to say, don't forget about thermal storage. And it can vary all over the place. In our tour yesterday, we drove by a park where there's a whole bunch of excavators right near the governor's mansion. They're doing a bunch of earthwork, and it's going to be a stormwater detention area because of the flooding issues. And you know, they're digging this bowl that can accommodate a lot of water. Well, we looked at that and said, you know what, we could put vertical loops in that, slinky loops in that shallow, and when that thing fills up with water, there's going to be a tremendous thermal volume there, tremendous thermal capacity. And it'll be grass on top, no moving parts. It could be a win-win, and it's right where we need it for some of these projects. So thermal storage, and like the seminar I mentioned just before lunch, the value of thermal storage, a lot of these things, in my mind, are not the total solution to just do a wastewater energy transfer. But when we combine them with vertical bore fields and other forms of thermal storage, when we can trickle charge, if you got a 100-ton load that doesn't sound like a big cooling load, you got a little data center, but that data center runs all the time, and you got a system that's heating dominant, but you got 24 hours of 100 tons going into that system. That can be big. And so even the little loads, pay attention, because if they go long enough, they can really provide value. And with that, I'm on my last slide. We've talked through air source, several wastewater options, stormwater, surface water, potable water, irrigation water, thermal energy transfer. No to my driller friends, I'm not saying give up your rigs. I love rigs. I love to play in the mud. It honestly makes most of these projects work. So I think drilling is still a wonderful deal. And with that, I'm ready for questions.
Hello, Sarah. This is a very good presentation. This is Pete Skinner. One thing you didn't mention that we don't hear very much about is the thermal value of heat of fusion. There was a North Dakota or South Dakota fellow who put a big tank in the backyard and buried it and put in swimming pool panels in an appropriate dimension. Okay. And left for the winter.
Sure.
Came back and found, oh no, my water-to-water heat pump is taking heat from a frozen tank. He then turned, it had a solar system.
Right.
And the solar system melted the ice and recaptured a tremendous amount of the heat of fusion.
Yes.
Have you ever used any of the PCM or other kind of things to enhance thermal storage? Thanks.
Yes, so, and there's been a lot of work done in this, also picking optimum PCM melt temperatures. Maybe we don't want to do it at 32. What if we did it at 45 or 75 or 100? And so it's an option. There's a project in New York that one of the ERLOBs just completed, a ground source, big high-rise, ground source. They didn't have enough footprint under the building for the bore field, and they couldn't quite handle the cooling peak load with the bore field. He put on air-cooled chillers with ice tanks, and at night they made ice, and then they melted that ice in order to unload the bore field and help it get by. I think there was a question, comment over there first? Okay.
I was just wondering if there's any significance to that single pipe loop, the ambient loop, the in and out of that. Was there any significance to upstream, downstream connection?
Yeah, in fact, could you bring that mic down to that guy holding up his hand? And he's going to answer that. Because he's done more of them than anybody I know.
You're going to have to ask a question again.
I'll ask it because I'm on the mic.
All right.
The question was, with the connections from the building or the heat source sink to the single pipe loop, what is their special guidelines? What should it be, upstream, downstream?
They are directional, and the upstream pipe is the feed for the building or the device. The downstream is the get. Technically, to do it properly, the connection should be back to back, and that way you do not induce flow into an hydraulically isolated circuit. But I wanted to make a comment, Steve, to help you out on the potable water, to an individual house. The standard answer we've gotten from the water authorities is, how do we, once you put one in, who gets the next one and who gets the next one? And pretty soon you do run out of capacity. And they can only stand about a 5-degree delta T because of the bacteria that are in there are sensitive to the temperature and everything else, and they help purify things. However, if you were to turn around and take that same system and look at it as charging a one-pipe loop,
Right.
sit around, it's entirely logical that we can turn around and set the temperature we are able to take from the potable water to feed it, and that can be either positive or negative.
Yep.
And so we have a solution for it. It doesn't rule it out, but we have a solution.
Perfect. Thank you, Kerry. All right, other questions?
One more.
Over here? Oh, we got two. I don't know who was first.
We only got one more because we're jumping directly into the next session at 2.
Got it.
In your initial slide, you included cooling towers.
Yes.
As a possible source. I've seen a small amount of chatter about people moving away from cooling towers. I guess I was looking for another data point about whether that is real or relevant or justifiable.
Many clients don't want water-cooled devices, so we see them applied in higher capacity applications. They're going to give you a little higher efficiency on your chiller, but the client's got to be willing to handle the chemical treatment requirements, the potential for Legionella, the noise, the vibration, the cost, the maintenance. But we see definitely a trend of fewer cooling towers and changing in technology. So we're seeing more and more closed-circuit cooling towers that are using adiabatic cooling processes that sometimes run with water and sometimes don't, if you got to do it. Thank you. Thank you all. Have a great day.